Hello, I'm Seema and welcome to part 33 of the chapter Organic Chemistry, Some Basic Principles and Techniques. We were doing the various methods of purification of organic compounds, and in part 32 we were discussing distillation. And I told you about simple distillation and fractional distillation. So moving ahead with our discussion about distillation, in this video I'm going to tell you the other two kinds of distillation, that is distillation under reduced pressure and steam distillation. So in this video I'll be telling you about these two. In simple distillation, we understood that this is a process of separation that is based on the property, that is the difference between the boiling points of miscible liquids. That you have liquids that mix with each other, and since they have different boiling points, you can put them all in a flask and you can heat them together, and that liquid or that compound that has the lowest boiling point will turn into vapors first. So that'll pass through the condenser and we'll condense it and separate it out as a liquid. Then we keep maintaining the temperature at the boiling point of the lowest boiling liquid. Then we raise the temperature, bring it to a little higher boiling point, as let us say we had a mixture of 3 compounds. So we'll bring it to the boiling point of the second compound. So the second compound will boil over and then it will get collected. And finally, the third compound, which has the highest boiling point, you can boil that and get the vapors of that, condense them and collect the third compound. And if there are some insoluble impurities left, they would remain in the flask. So this was the basic procedure of simple distillation. And the details of it, why we do fractional distillation, the details and the intricacies of the distillation, I guess you would understand if you watch video number 32. But using that information, that basic information that we have, that distillation is based on separating compounds which have got different boiling points, let us understand these two distillations too. Now, in order to understand the different kinds of distillations, or the ones that we are going to study now, it is first important to understand what boiling point of a compound is. You know, we have often heard that water boils at 100 degrees Celsius at 100 degrees Celsius at the sea level, or at 1 atmospheric pressure. When the pressure of the atmosphere is 1 atmospheric pressure, water boils at 100 degrees Celsius. Boiling point is actually that temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure. When you have a vessel and there is water boiling in it, the gases of the atmosphere are pressing the liquid downwards, and the vapors that are produced due to the energy that they've gained from the heat, from the burner that you're using, as the water is boiling, the molecules that turn into water vapor, it comes up, it moves upwards and pushes against the atmospheric pressure. So atmospheric pressure is pushing them down and the vapors are pushing it upwards. When the atmospheric pressure becomes equal to the vapor pressure, now there is no push or pull. No one is pushing anybody down. No one is, because both of them are the same pressure. At that point, the liquid starts, like water, it starts boiling and it starts getting converted into the vapors or the gaseous phase. So that is how we define boiling point. So the boiling point is that temperature. So in the case of water, what is the boiling point? We usually say it is 100 degrees Celsius at 1 atmospheric pressure. So when the pressure is 1 atmosphere, which is usually at sea level, the water boils at 100 degrees Celsius. In other words, at 100 degrees Celsius, the vapor pressure of water becomes equal to the atmospheric pressure and therefore boiling starts. In the case of a pressure cooker that we use for cooking, why does food cook faster in a pressure cooker? It cooks faster in a pressure cooker because it is a sealed vessel. So now we are boiling water along with the vegetable. Let us say I'm boiling potatoes. So if I am boiling potatoes in this, I add water and the potatoes and I start heating the pressure cooker. And the lid is sealed. If you notice, a pressure cooker has a gasket in it. So it seals very well. And since it seals very well, it does not allow even air to pass through it. So now we have an isolated system. In this isolated system, when the water starts boiling, it's producing the vapor pressure, but the atmospheric pressure is not pushing it down. Rather, we have the lid. So the vapor pressure actually becomes greater than the atmospheric pressure. And since it becomes higher than the atmospheric pressure, the water is actually not at 100 degrees Celsius, it is even higher than 100 degrees Celsius. So since the liquid, that is water inside the pressure cooker, is boiling at a temperature higher than 100 degrees Celsius, the potatoes, they cook faster in a pressure cooker. On the other hand, if I just took a vessel and I put the potatoes in water and I allowed it to boil, it might take more than half an hour to boil. But in the pressure cooker, I might do it in just 5 to 10 minutes. My process is speeded up. Why? The cooking is speeded up. Why? Because the water inside the pressure cooker is boiling at a higher temperature. Now the question is, why am I telling you the story of cooking food when our topic of discussion is distillation? The reason I'm telling you this is that we can manipulate the boiling point of a liquid. And how can we manipulate the boiling point of a liquid? We can manipulate it because we know that boiling point is that temperature at which the vapor pressure becomes equal to the atmospheric pressure. If we change the external pressure, which in the normal case is atmospheric pressure, if we change the external pressure, we can change the boiling point. In the case of the pressure cooker, we increased the pressure by pressing it, by not allowing the vapors to escape to the atmosphere. Therefore, the pressure was far higher and therefore the water was boiling at a higher temperature. We can do the reverse of this. Imagine if I wanted to boil water at a lower temperature, what should I have done? Here I increase the pressure by putting a sealed lid on top of the pressure cooker. If I somehow had a way of reducing the pressure instead of increasing it, my water would have boiled at a lower temperature. Am I right? I could have done the opposite and acquired the opposite result. And that is what is done in the case of distillation. What is distillation? It is boiling a liquid and then collecting the vapors, condensing it and turning it back into a liquid and thus separating it. So distillation is nothing but actually boiling. So boiling under reduced pressure. If you reduce the pressure, what will happen now? When we increase the pressure, the boiling point of the liquid increased. And if we reduce the pressure, the boiling point of the liquid should decrease. So, distillation under reduced pressure is done for those compounds whose boiling point is very high. It is so high that you feel that you're wasting too much of fuel just vaporizing it and then condensing it and then collecting it. So instead of wasting so much of fuel just to bring it to its boiling point, if we could somehow manipulate it to make it boil at a lower temperature, would it not be smarter? So this distillation under reduced pressure is a smarter distillation. Smarter than simple distillation. Actually, all the distillations other than simple distillation are smarter distillations. Simple distillation is the actual distillation. Fractional distillation was the smarter version where we repeated the distillation by increasing the length of the column, so that the vapors, as they rise, the different fractions keep separating out. And as the vapors rise, they keep cooling down and we keep getting the different condensed fractions. And distillation under reduced pressure is again the smarter way, that we are going to distill it, but at a lower boiling point. So distillation under reduced pressure is done, it is used to purify liquids with very high boiling points. One situation is that the boiling point is very high and you want to make it easier. You want to save fuel, you want to save time. And then there is another situation in which you may use distillation under reduced pressure. Some compounds, organic compounds are covalent compounds. They are not ionic compounds. They are not very strong bonds. Covalent bonds are not that strong. So if the boiling point of a substance is high and you boil it, there is a possibility at that temperature the bonds of the molecule may break. And if the bonds of the molecule break, the compound is no longer the same compound. It has decomposed. It has broken down. So those compounds which either have a very high boiling point or those compounds that decompose at or sometimes even below the boiling point. It hasn't even achieved the boiling point. Before that itself, it started decomposing. So for such compounds, we use distillation under reduced pressure. So they decompose or below, or those that decompose at or below their boiling point. For such compounds, we use distillation under reduced pressure. Now, what is boiling point? How is it defined? Boiling point is that temperature at which vapor pressure is equal to the atmospheric pressure. Now, this is the apparatus that you have in the laboratory to carry out this process, that is distillation under reduced pressure. How can you reduce the pressure? In the case of pressure cooker, it was simple. All we had to do was add a lid to seal it off and build the pressure inside the cooker. But if I had a pipe here and I connected it to a vacuum pump which would suck out the vapors that are being formed, then in that case I am reducing the pressure. So the apparatus is the distillation apparatus, but here you connect it to a vacuum pump. And when you connect it to a vacuum pump, the entire apparatus, if you really see, here you have the liquid that has to be distilled. And all this, you have vapors which then condense and droplets of it are coming down. But all of this is like an air chamber above it. So if we connect this end of the flask to a vacuum pump, we can actually create a lower pressure in the entire column above the liquid. And when the pressure becomes lower than the atmosphere, if the vessel was open, if this flask was open, then the pressure would have been atmospheric pressure. And the vapors would actually have escaped from this. We don't want that, so we seal it up. And we seal it and we connect this end to a vacuum pump. And since we connect it to a vacuum pump, we suck some of the air out of it so that the pressure becomes lesser. And now when you boil it, the boiling will take place at a lower temperature. So you take the organic compound which has to be separated and by distillation under reduced pressure, and then there is a capillary here which is used to regulate the pressure, regulate the air pressure here. So if you feel that the air pressure is too less and you want the liquid to boil at a slightly higher temperature, you want to maintain a certain temperature, so you can add a little air by opening the stopcock and letting a little atmosphere, that is the air, regular air, come into it. But with the help of the vacuum pump, you are maintaining that pressure. On one hand, you can suck the air, in the other hand, you have a stopcock which can allow a little air to come in. So now, you start boiling the mixture, and when it boils, the compound which is boiling it again, it is like simple distillation. The only difference is that here the compound is boiling at a temperature lower than its boiling point, and the rest of the process is the same. The vapors rise, they are condensed and it's collected as when it passes through the condenser. What is the condenser? The condenser is a glass jacket over the tube, over the delivery tube. So this glass jacket, you allow cold water into it, and cold water coming out, it circulates around the inner tube in the form of a jacket, and turns the vapors, it cools down the vapors which get condensed and come down as droplets and are collected. An example where distillation under reduced pressure is where glycerol, which can be separated from spent lye in soap industry. When you prepare soap industrially, the byproduct of soap is glycerol, and glycerol can also be used for other things. So this byproduct is also pretty useful. So this glycerol, it can be separated from the spent lye of the soap, the waste of the soap. In the soap industry, the spent lye is separated, the glycerol is separated from the spent lye with the help of distillation under reduced pressure. Now, there are two laws that are applicable when you carry out distillation. One is Raoult's law, which says that the vapor pressure of a liquid would be equal to the vapor pressure of the liquid in its pure state into the mole fraction of a liquid in the mixture. Now, Raoult's law is only applicable to those distillation processes where the liquids are miscible. You should have a mixture of liquids which dissolve in each other, miscible liquids. And Dalton's law of partial pressure says that if you have two liquids, then the total pressure would be equal to the partial pressures, partial vapor pressures of each of the liquids. So if you have two liquids in the mixture, in a miscible mixture, then the vapor pressure of one plus the vapor pressure of the other would be equal to the total vapor, total pressure. That is the total gaseous pressure. Why am I mentioning these here now? Because till now we have done distillation of compounds where you have miscible liquids. The fourth kind of distillation which we are going to discuss now, that is steam distillation. Steam distillation is carried out for compounds which are not miscible with each other. They do not dissolve in each other. In that situation, Raoult's law is not applicable. Raoult's law is no longer applicable, but Dalton's law is. I would not go into the details of this because it is not there in your syllabus. Yet, there's no harm in mentioning it right now, so you have a little idea that when you have, it is this steam distillation where Raoult's law is not applicable, but Dalton's law, of course, of partial pressures is always applicable. So now we talk of the fourth distillation, that is steam distillation. In steam distillation, this is used to separate steam volatile substances which are immiscible in water. What do you mean by that? The substances is steam volatile. Volatility means turning into vapors. Steam, it vaporizes in the presence of steam. It is immiscible, it does not dissolve in water. But in the vapor state, it can vaporize along with the vapors of water. You know, in this kind of a distillation, water is not actually one of the components that you're using to separate. Water here is only a medium actually, which helps you to vaporize that compound that has to be separated. So it is used to separate steam volatile substance which is immiscible in water, but it is miscible, that is, it is volatile in the steam state. It can mix in the steam state, but when it is water in the liquid state, it does not dissolve in it. So what would you have in such a distillation? You would have water, because we're talking of steam volatility. We are using water in the form of steam in order to pick up the vapors of that liquid, turn that liquid into vapor and pick it up along with the steam and pass it for distillation. And the substance has, let us say it is an immiscible oil. The compound that you have is an immiscible oil because oils do not dissolve in water, and the oil has some other immiscible impurity in it. It has some miscible or immiscible impurity in it. Now, so what do you have in the flask? You have water, you have oil which does not dissolve in water. In the first flask you only have water. And in this flask you have the oil and that compound, the immiscible oil and the non-volatile liquid. So, what do we do? In the first flask we have water and we start boiling the water. When water starts boiling, the vapors of water rise and they come into the second flask, which actually has the compound, impure compound that has to be distilled. So what happens? The water that comes in, do you see we have not added a condenser here? There is no condenser. We want the vapors to come in, and we have a thermometer here to check what temperature is it. The water starts boiling and we allow it to come down, the water vapors come down, and this substance, in the presence of water vapor, due to that heat, we are heating this also. In the presence of the water vapor, along with the water vapor, the vapors of this liquid also start rising. Now, this is where Dalton's law comes into play. Why did I mention Dalton's law? According to Dalton's law, total pressure is equal to the vapor pressure of the individual gases. So in this flask, you have vapors of water. So water has a vapor, the water vapor has a pressure of its own. And this liquid, the immiscible liquid or the oil that you were boiling, that also has a vapor pressure. We know the boiling point of water is 100 degrees Celsius. So the water, if it is boiling at atmospheric pressure, then the water vapor is at 100 degrees Celsius and by the time, let us say, it came down here, it cooled slightly. But in this flask, the total pressure is equal to the vapor pressure of steam, that is the water vapor that came here, plus the vapor pressure of this liquid. So the pressure in a way is increased in this flask. And since the pressure, due to this pressure, although total pressure is increased, the P total is increased, the vapor pressure of this liquid need not be the total vapor pressure, atmospheric pressure, because some of the pressure is being contributed by steam. So this liquid starts boiling at a lower temperature. Why? Because it does not need so much vapor pressure. It only has to contribute partial vapor pressure, and both the vapor pressures together will become, the vapor pressure will become equal to the atmospheric pressure. So you have vapor pressure of water and the vapor pressure of this liquid, this oil. Even below its boiling point, it will start turning into vapors. And when it turns into vapors, both the vapors, that is water vapor, and the vapors of this oil, they carry through the pipe here. And we put a condenser, just like regular distillation, we condense it, and when we condense it, we start collecting the liquid. But the liquid that we have is the immiscible oil that vaporized and water. But these two do not dissolve in each other. So we will get, in this flask, what we get, the distilled liquid will consist of two separate layers. One will be the water layer, and the other will be the water, and other would be oil. I made a mistake here. Water should not be on top. Oil usually floats over water. So the lower layer should be water and the upper layer should be oil. So in this flask, you will get two layers, the layer of water and the layer of oil. Now, why did we carry out this distillation? Because in the end, we did not get a pure substance. It seems to be crazy. But the truth is that the impurity, the non-volatile impurity which was mixed in the oil, did not vaporize and did not go here. So you used water only as a medium, and the water only helped to pick up the oil in the form of its vapors and separate it out here from the impurity, and the water and oil that got collected separately was put into a separating funnel. And in the separating funnel, what does the separating funnel look like? The separating funnel is somewhat a flask like this, with a little tap in the bottom, an opening here, a stopcock, right? So what you do in a separating funnel, it has a stopcock. So the oil and water mixture, you fill it up here. The oil will be floating on top and the water is here in the bottom. So let us say this is the layer. You open the stopcock at the bottom and we find that the water starts coming out, and we slowly open the stopcock. As it comes here, we open it very little so that drop wise the water comes out and you are left with just one, maybe one odd drop of water, and the rest is oil, and we turn off the tap. The stopcock is closed. So that is how you will separate out the water and the distilled liquid. So in the case of steam distillation, what did we do? We just used water as a medium to help vaporize the oil at a lower temperature and separate it from the non-volatile compound. So this was steam distillation. So let us say that P1 is the vapor of the steam volatile liquid. The steam volatile liquid is the immiscible oil, and P2 is the vapor pressure of steam. Then P is atmospheric pressure. The vapor pressure of steam and the vapor pressure of the steam volatile liquid together would form vapor pressure, and that is the reason why this liquid actually boils at a temperature lower than its boiling point. In this case also, in distillation under reduced pressure also, the substance was boiling at a temperature lower than its boiling point, but that was because we decreased the atmospheric pressure by connecting it to a vacuum pump. But in this case, we did not connect it to a vacuum pump, rather we substituted some of the atmospheric pressure with the help of the vapor pressure of water. So water vapor will contribute some of the pressure, so the liquid, the immiscible liquid, only has to contribute part of the vapor pressure to become equal to the atmospheric pressure. Therefore, it boils at a lower temperature. So these were the two topics that I had to do. With this, I'll wind up today's video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos on chemistry. Thank you for watching, and bye-bye for now.